In the previous lecture, we discussed some properties of systems, and in particular, we talked about 6 properties of systems. The first was whether a system has memory or not, so whether a system is a system with memory or a memoryless system. Then we talked about the invertibility of the system, and the third property was the causality of the system. The fourth property we discussed was the stability of the system. The fifth property we talked about was time invariance property of the system, and finally the sixth property we talked about was the linearity property. And at the end of the last lecture, I mentioned that in particular terms we'll be discussing in much detail about linear time invariant systems, that is, systems which satisfy the properties of linearity and time invariance. Okay, such systems are important because many physical systems in the real world satisfy these properties, and therefore we can represent real world processes as linear time invariant systems, or we call abbreviated as LTI systems. L for linear, T for time, and I for invariance, right? So that's linear time invariant systems. And the other important reason why we focus LTI systems in detail is because LTI systems satisfy the superposition property that we have seen earlier. Now, just to recall very quickly, what is the superposition property? Basically, what it says is that if an individual input gives a specific individual output, then if we give an input which is a combination of these individual inputs, then for an LTI system, the output of that combined input signals will be a combination of those individual outputs as well. So that applies to both the discrete time case as well as the continuous time case. So what we are saying is that if we create a new signal which is a linear combination of these input signals x1, x2, x3, and so on, the output of these combined signals, of the signal which is combined version of these individual signals, will be a combined version of these individual outputs as well. So that is what we mean by the superposition property of systems. So basically what we are saying is that if we have a system with a new input x of n, which is a linear combination of x1, x2, x3, which is nothing but it is a linear combination of scaled and added versions of each of these individual components. So a1 x1 of n plus a2 x2 of n plus a3 x3 of n, and so on, for all values of k. In general, summation ak xk of n. So if that is our input signal to the LTI system, then the corresponding output y of n is also a linear combination of the individual outputs y1, y2, y3, and so on. So that applies again to both the discrete time system as well as the continuous time system. So a system that satisfies the superposition property, where that is basically the a linear combination of inputs produces a linear combination of corresponding outputs. Okay, and LTI systems satisfy this property. So therefore, it becomes easier to analyze LTI system, because if we have any input signal x of n, and if we can represent that x of n in terms of some simple input signals x1, x2, x3, and so on, and if we know the output of the system for each of these x1, x2, and up to xk, then we can find the overall output of that system to that input signal x of n by a linear combination of those individual outputs which are produced when we give x1 of n as input or x2 of n as input, right? So the superposition property helps and makes it easy to analyze an LTI system, because LTI systems satisfy the superposition property. So if we want to find the output of any complex signal x of n, if we can break down this complex signal x of n into simpler signals x1, x2, x3, then all we need to do is we need to find out what is the output of that simple signal x1 of n, what is the output of the simple signal x2 of n. If we know those outputs y1, y2, and so on, we can find the overall output y of n when the input is x of n by getting a linear combination of the individual outputs. So that is why LTI systems play such a huge role. Now, for that, what we need to see is that how can we represent any signal x of n in terms of some simple signals x1, x2, x3, or in general in terms of some simple signal xk of n. So that is what we are going to see now. And the first thing I want to highlight here is that we'll focus on the discrete time signal, and later on we'll move to the continuous time signal. So any discrete time signal can be represented in terms of the delta function, which is the unit sample function, also called as the discrete unit impulse signal. So I've depicted an arbitrary signal x of n here, and we want to try to represent this x of n in terms of the delta function delta of n, or which could be delta of n or shifted versions of delta of n. So x of n is some arbitrary discrete time signal which I've defined for from -4 to +4. And what we have on the right hand side is the delta function, which is having a value of 1 when n equal to 0. And the second plot here is also a delta function, but it is shifted to the left by 4. So instead of at 0, it is this delta n shifted to the left by 4 index units of n. So this is basically equal to delta of n plus 4. Okay, so plus means shifted to the left. Similarly, this one corresponds to being delta of n plus 3, because it is this delta of n shifted to the left by 3 sample units, or 3 index units. So this is delta of n plus 3. So basically what it means is that delta of n is equal to 1 only when n equal to 0. Delta of n plus 4 is equal to 1 only when n equal to -4. That is, at n equal to -4, it is having a value of 1. For all other values, it's 0. And delta of n plus 3 likewise is having a value of 1 when n is equal to -3. So at -3, it is having an impulse of height -1, of height plus 1. So basically now what we are going to do is we are trying to represent this signal x of n in terms of these delta functions. Okay, so what we are going to do is I've just depicted for 3 cases here: when n equal to 0, when n equal to -4, and when n equal to -3. Similarly, you can have a shifted version delta of n plus 2, which will be at -2, delta of n plus 1, which will be at -1, delta of n is at 0, delta of n minus 1 will be at +1, delta of n minus 2 will be a shifted version of delta of n at 2, and so on, right? So we can therefore write this signal x of n in terms of these delta functions. So what happens if I take this signal x of n when n equal to -4 and multiply it with delta of n plus 4? So basically I'm going to take this. So this is our x of -4. Now if we take the x of -4 and multiply it with delta of n plus 4, so we'll multiply it with delta of n plus 4. What do we get? We get basically this value, this product is going to be non-zero and equal to x of -4 only when n is equal to -4. For all other values of n, delta of n plus 4 is 0. So multiplying this value with delta of n plus 4, this is equal to, okay, the height of this is 1. So it's basically multiplying this value with 1 when n equal to -4, and for all other values it was going to be multiplied with 0. So we'll get exactly this impulse. So this is basically representing this particular impulse here, which is x of -4 in terms of the delta function, which is shifted to the left by 4. Similarly, we can represent this x of -3 by multiplying this x of -3 with delta of n plus 3. So when n equal to -3, we'll get x of -3 multiplied with delta of n plus 3, which is 1 at that value of n. So this value into 1 is equal to the same value, And for all other values of n, it's going to be this value multiplied with 0, because for all other values of n, delta of n plus 3 is 0. So we can now add up this term to the first term now, right? So that will become plus x of minus 3 into delta of n plus 3. And similarly, for x of minus 2, we can multiply it with delta of n plus 2, which will be a delta of n shifted to the left by 2. So we can keep adding these terms, so it will become plus x of minus 2 multiplied with delta of n plus 2, and plus x of minus 1 multiplied with delta of n plus 1, plus x of 0 multiplied with delta of n, because when n equal to 0, we multiply this term, this impulse here, with this delta of n directly, because this is not shifted, because we want the index for n equal to 0, and plus x of, so when n equal to 1, so we'll write it as x of 1 into delta of n minus 1, because corresponding to this, if you want to multiply this with the delta at n equal to 1, that is going to be this delta of n shifted to the right by 1. A right shift corresponds to minus in this argument here. So delta of n minus 1 is nothing but an impulse at n equal to 1. So that's x of 1 times delta of n minus 1, and plus x of 2 times delta of n minus 2, plus x of 3 times delta of n minus 3, plus x of 4 times delta of n minus 4. So basically, we have represented our signal x of n in terms of the delta function, shifted and scaled delta function. So this is basically, this first term here is nothing but, let me underline this, this first term, okay, this first term here is nothing but this delta function shifted to the left by 4 and multiplied with some value which is equal to x of minus 4. So it is a scaled and shifted version of delta of n. Similarly, this second term here is a scaled and shifted version of this delta of n. It is shifted to the left by 3 and scaled by x of minus 3. Similarly, this delta of n plus 2 is a shifted version of delta of n to the left by 2 and scaled by a factor x of minus 2. So basically, we are representing this signal x of n in terms of shifted and scaled versions of this delta of n. So delta of n is our unit sample function, and we have now represented our input signal x of n in terms of shifted and scaled versions of the unit impulse function or unit sample function. So we can write this whole thing as a summation as x of n equals, so let me write that as a summation. So we can write our x of n as summation x of k times delta of n minus k. So if you look here, it is x of k times delta of n minus k. So n minus minus 4 will become n plus 4. So x of k is minus 3 here. So x of minus 3 into delta of n minus minus 3. So n plus 3 and so on. So it is x of k delta of n minus k. And we are summing it up for all values of k. So in this particular example, our signal is defined only for k equals minus 4 to plus 4. If there are samples to the left of minus 4 and to the right of plus 4 also, we need to include that. So for this particular example, our k value is ranging from minus 4, k k equals minus 4 to plus 4. So this, we have basically represented our input signal x of n in terms of shifted and scaled versions of the unit impulse function. And in general, okay, if our signal had values beyond minus 4 and plus 4, so in general we can represent our signal x of n as the summation of x of k times delta of n minus k for k equals minus infinity to plus infinity. Now let me write that infinity a bit clearly. That's minus infinity to plus infinity. Okay, so depending on for what values of k the signal is defined, okay, the discrete signal x of n is defined. Accordingly, we can represent our signal x of n in terms of shifted and scaled unit impulse function. So delta of n minus k is nothing but a shifted version of delta of n, and x of k is getting multiplied with that shifted version, so it's getting scaled by a factor x of k. So we have represented our signal in terms of the scaled and shifted versions of the impulse function. Okay, this is basically representing the input signal x of n as a linear combination of the unit impulse function. So basically what this means is that as we go through this equation for different values of k, this expression is extracting the values of the x of n at each value of k, right? So where, for example, if I take this previous example of x of n, which has values from minus 4 to plus 4 for n, so when k is minus 4, we get x of 4 into delta of n plus 4. So when we multiply these two, what do we get? We will get a non-zero output for this product only when n equal to minus 4, or when this argument is minus 4. When k is minus 4, so x of minus 4 and correspondingly delta of n minus 4 is and delta of n plus 4. And when they get multiplied, we get x of minus 4 multiplied with 1, which is equal to x of minus 4. So the product of these two will simply give us x of minus 4 times delta of n plus 4. So we'll have it something like this. So at n equal to, that's minus 1, minus 2, minus 3, minus 4. So at n equal to minus 4, we'll have this value like this, because that is the only value of n for which you have a non-zero value for delta, right? So when this argument is k equal to minus 4, that is the only value for which this delta of n plus 4 is non-zero. So x of minus 4 times delta of n plus 4 will give us exactly what is available at x of minus 4. So this signal here is basically x, the n on the x-axis, and what we have plotted here is nothing but x of minus 4 times delta of n plus 4, right, which is nothing but the first term that we have here in this summation, x of minus 4 times delta of n plus 4. It extracts this particular value of x of n. Okay, similarly, if we multiply x of minus 3 with delta of n plus 3, it will extract this particular value of x of n. And this equation, which extracts each of these impulses, each of these values of x of n separately, this equation which gets that process done, this is called as the sifting property. Okay, we call this as the sifting. All right. So basically what the sifting property does is that it extracts the value of x of n for each value of n separately. So x of minus 4 times delta of n plus 4 gives us only the value of x of n when n equal to minus 4. Similarly, x of minus 3 into delta of n plus 3, the next term for the next value of k, will give us the value of x of n for n equal to minus 3, and so on. So we are able to extract, that is separate out each of these values of x of n for individually by using this equation. Okay, so it is called as sifting, means separating out the individual components of that signal. So we call this as the sifting property, and this sifting property allows us to represent or we get this as a consequence of being able to represent our signal in terms of shifted unit impulses. And just to get this point clearer, where we are trying to represent any signal x of n in terms of or as a linear combination of shifted unit impulses. Let's take the example of the unit step function, which we have seen earlier, and we will try to represent the unit step function as a linear combination of the unit impulse function, or as a summation of shifted unit impulses. So let us now see how we can represent the unit step function as a linear combination of shifted unit impulses. So what we have on the right hand side here is the unit step function, which is having a value of 1 for n greater than or equal to 0. For n less than 0, it is 0. So it is only available for positive values of n. And clearly each of these is having a height of 1. And we can represent this unit step function as a summation of these shifted delta functions, right? So this is nothing but delta of n. This impulse here, that is u of 0, is nothing but delta of n. This u of 1 is nothing but delta of n minus 1. If we shift this and bring it here to the right, shift it to the right by 1, you get this impulse which is here, which is nothing but u of 1. So similarly, we get u of 2 and so on. So that means if we just add up all of these terms, for that is delta of n plus delta of n minus 1 plus delta of n minus 2 plus delta of n minus 3 plus delta of n minus 4 and so on up to infinity, we will get the unit step function. So basically, multiplying we can represent these the unit step function as a linear combination of shifted impulses. That's the impulse without any shift. That's an impulse shifted to the right by 1 index unit. That's an impulse shifted to the right by 2 units and so on. So basically, if we add these all together, we will get the unit step function. So we can say that we can represent the unit step function u of n as delta of n plus delta of n minus 1 plus delta of n minus 2 and so on. So that's delta of n plus delta of n minus 1 plus delta of n minus 2 plus more terms, right, up to infinity. Or in general, we can write in short form notation, we can write the unit step function u of n as a summation of delta of n minus k, where k goes from 0 to infinity. So when k equal to 0, we get delta of n minus 0, which is delta of n. And for k equal to 1, it's delta of n minus 1. For k equal to 2, it's delta of n minus 2 and so on. So basically, we are representing the unit step function in terms of the shifted impulse functions. And the scaling factor here, shifted and scaled version, right? The scaling factor here in this case is 1 for all the shifts. So delta of n is getting multiplied with 1. Delta of n minus 1 is multiplied with 1. Delta of n minus 2 has an amplitude of 1. All of them have the same amplitude. So they are all, their scaling factor or the weights are in the linear combination are all equal to 1 in this case. Unlike in the previous case where we had these x of k as our scaling factors or weights. Okay, so x of k is the weight of each of the shifted impulses. In this case, for the unit step, each of the weights for the shifted impulse is equal to 1. So we have represented the step function as a linear combination of the impulse functions or shifted impulse functions, And therefore, basically what we're trying to do is, if you are able to represent any signal in terms of simpler signals, then if we know the output to a system for this impulse, then we can also find out the output for the system for any other signal which is represented as impulse, because by the superposition property, if I know what is the output for delta of n, and for delta of n minus 1, and for delta of n minus 2, and so on, then the overall output will be the output of delta of n plus the output of delta of n minus 1 weighted by the same factors. Okay, so that is why LTI systems are make such an interesting topic. So and that is exactly what we are going to demonstrate and show, that how can we find the response of a system, of an LTI system, if we know the response of the system to the unit impulse function. Now, to proceed further, let us also recall the property of time invariance. So for a time invariant system, again, this is something which we discussed earlier. If the system is time invariant, for example, if a input signal x of n produces an output signal y of n, okay, then if the input is shifted by some amount, say n naught, to the right, then the output will also be the previous output y of n shifted by the same amount. So that's going to be y of n minus n naught. If the input is shifted to the left, for example, n plus n naught, then correspondingly the output will also be shifted by the same amount, y of n plus n naught. So for a time invariant system, if we know the output of the system y of n for some given signal x of n, then the output for a shifted version of that input will be the same as the shifted version of the previous output, right, of the original output y of n. So whatever is the shift produced in x of n, and the corresponding output y of n will also be shifted by the same amount that has been introduced into the input signal. So this is a property for the time invariant system, and we will be using this in developing an important concept in signals and systems. So to illustrate that, what I'm going to do now is I'm going to give you a system to which we are going to apply the shifted unit impulses. So we'll take a system and give an input delta of n. We'll give an input delta of n minus 1, delta of n minus 2, and also shifted versions to the left as well. Okay, and we will see what will be the how we can represent the overall output of a system given the response of the system to such impulses. So let us now consider that we have an LTI system, and the input to this LTI system is a unit sample function or a discrete unit impulse function. Okay, so that means it's delta of n, which has a value of 1 for n equal to 0. For all other values of n, it is equal to 0. So if we give this delta of n as input to the LTI system, it produces some output, and this is a special output. The response to a system produced when the input is an impulse function is called as an impulse response, and it is denoted by the letter h of n. So the impulse response, the standard notation for denoting the impulse response of a system is h of n. Okay, let me write that properly. Okay, it's h of n, and it's h of n is called as the impulse response of the system, because it is the output of the system when the input is a unit impulse function. So we call it as the impulse response of the LTI system. So when the input is delta of n, the output is h of n. And if the system is time invariant, any shift in the input will produce a corresponding shift in this output. Okay, so if you know what is the output for delta of n, then the output for when the input is a shifted version of delta of n will be a shifted version of h of n, as we have seen, as we have depicted in these equations here, right, in these expressions over here. So if we shift this impulse to the right by some amount, then this h of n will the response will also be shifted to the right by the same amount. If we shift this impulse to the left by some amount and give as input, then this h of n will also get shifted to the left by that same amount, and that comes from the fact that this is a time invariant system. Okay, so let's see what will be, or let's try to depict what will be the output of the system if the input gets shifted by a certain amount. So we have seen that when the input is delta of n, the output is the impulse response h of n. If the input is shifted version of delta of n, here we have shifted it to the right by 1, so this is delta of n minus 1, then what will be the output if this is a linear time invariant system? So by the time invariance property, if the input is shifted, then the corresponding output is also shifted by the same amount. So basically we'll have it as h of n minus 1. So basically what it means is that if we know what is the output for this unit impulse, then we know the output for shifted versions of it as well. We don't need to check what is the output. If we know this h of n, all we need to do is shift this accordingly depending on how much the input has been shifted. So if it is delta of n minus 1, then the corresponding output is also shifted by the same amount to the right. And in this case, in the third case here, we have shifted the input to the left by 1, so it is an impulse at n equal to minus 1, so that's delta of n plus 1. In that case, the output of the system is a shifted version of the impulse response shifted to the left by 1, that's h of n plus 1. Okay, so by the time invariance property, the output of the system, the impulse response of the system to shifted versions of the impulse at the input is basically the shifted versions of the impulse response itself. Okay, so if there is any shift in the input signal, there is a corresponding shift in the output impulse response as well. So when there is no shift here, we got h of n. When delta of n is shifted to the right by 1, h of n has also got shifted to the right by 1. When delta of n is shifted to the left by 1, the h of n has also got shifted to the left by 1, and that is a property coming from time invariance, right? Let me write this n properly. So this is h of n plus 1. Now if we have a new input, which is a linear combination of delta of n and delta of n minus 1 and delta of n plus 1, and in this linear combination I'm going to make the weights of the linear combination all to be equal to 1. So basically we are going to create a new signal x of n, which is basically the sum of these three signals, delta of n plus delta of n minus 1 plus delta of n plus 1, and then see what will be the corresponding output of that system, given that we know the outputs of these individual signals, right? So basically we are going to have an input signal which is going to be defined as an impulse at n equal to 0, an impulse at n equal to 1, and an impulse at n equal to minus 1. It is basically a combination of these three signals. This is an impulse at n equal to 0, an impulse at n equal to 1, and an impulse at n equal to minus 1. I have just combined them. So this is our new input signal, x of n. So we'll call this as x of n, and all of them have a height of 1. Okay, so this is 0, 1, minus 1. Okay, if this is given as input to our system, what will be the corresponding output? So now basically we have a signal x of n, which is a linear combination or which is represented in terms of shifted versions of the impulse function. If this is given as input to this LTI system, since we know what is the output when the input is delta of n, that's h of n. What is the output when the input is delta of n minus 1, and what is the output when the input is delta of n plus 1. So we have all of this here. So if the input is a linear combination of these inputs, then the output is a linear combination of these outputs as well. The only difference here is that this x of n is equal to, let me write that, delta of n minus 1 plus delta of n plus delta of n plus 1. So it is represented as a linear combination of the inputs, delta of n minus 1, delta of n, and delta of n plus 1, where the weights or the scaling factors are equal to 1. It's 1 times delta of n minus 1 plus 1 times delta of n plus 1 times delta of n plus 1. So the overall output of this system is going to be a linear combination of these individual outputs, that is h of n plus h of n minus 1 plus h of n plus 1, right? So we will get this output, which is the summation of all these three individual outputs. So h of n minus 1 plus h of n minus 2 plus h of n, not minus 2, h of n minus 1 plus h of n plus h of n plus 1. Okay, so basically it's the summation of these three outputs. I'm just keeping the central value n in the middle and minus 1 and plus 1 to the other sides, right? Or vice versa. It doesn't matter. Okay, we are just adding up the terms. Generally we'll keep the right shifted versions to the right and the left shifted versions to the left, in which case it should actually be n plus 1 here. So let me just make that correction. So that will be n plus 1 delta of n, and this will be delta of n minus 1. Okay, so we have put delta of n in the middle, delta of n minus 1, which is the right shifted version, and delta of n plus 1 is the left shifted version. Okay, you can write it either way, doesn't matter. Changing the order of addition doesn't change anything, but I'm just trying to be consistent. So this will be delta of n plus 1 plus h of n plus 1 plus h of n plus h of n minus 1. Okay, so basically, because it's an LTI system, if we know what is the input, what is the output when the input is delta of n plus 1, what is the output when the input is delta of n, and what is the output when the input is delta of n minus 1, then we can find the overall output of this x of n, which is a linear combination of these individual input signals, to be the linear combination of the corresponding individual output signals. Okay, now here we have put the scaling factor as 1. Now I'm going to take this one step further, where we will introduce some scaling factor in this linear combination. That is, the weights, we will make it as not equal to 1. We'll have some other values for these weights. So I'm going to give a new x of n, which will be, say, 4 times delta of n plus 1 plus 3 times delta of n plus 2 times delta of n minus 1, something like this, and see what will be the response to that system. So now we are going to introduce some scaling factors to these deltas. So for example, we are going to multiply this delta of n plus 1 with some number. Okay, this delta of n with some other number, and this delta of n minus 1 with some number, and those multiplying factors could be positive or negative. So what we have here is this delta of n plus 1. I have multiplied with 1. I've kept it as it is, so it is still an impulse of height 1. This delta of n has got multiplied by 2, so it is 2 times delta of n. So 1 into 2 became 2, so it is now having a height of 2. And this delta of n minus 1, which is a right shifted version, okay, this is delta of n minus 1, it is multiplied with minus 3, so it's minus 3 times delta of n minus 1. So it is flipped down, so it is multiplied with minus 3, so it's an impulse in the negative, with a negative height. Okay, so it's in the negative side here, right? So now basically we are saying that our x of n, our input signal x of n, is delta of n plus 1, which is this impulse, which is the same as this delta of n plus 1. We have not changed that. Delta of n has got multiplied with 2, so that's plus 2 times delta of n plus 2 times delta of n, and delta of n minus 1 is multiplied with minus 3. So we have multiplied this with minus 3, so we get minus 3 times delta of n minus 1, minus 3 times delta of n minus 1. Now, what will be the output of this system, given that we know what is the output when the input is delta of n, when the input is delta of n minus 1, and when the input is delta of n plus 1. We know that the output correspondingly is h of n minus 1, and h of n plus 1. So now the input is a shifted and scaled version of these individual inputs. So therefore the output will also be a shifted and scaled version of the individual original outputs, right? So the output y of n in this case, so the output y of n will be a linear combination of the original outputs shifted and scaled by the same amount. So when it is delta of n plus 1, so for delta of n plus 1, the output is h of n plus 1. So, and that has not got scaled, so that will still be h of n plus 1. When the input is delta of n, okay, when the input is delta of n, the output is h of n, but now the input has got scaled by a factor of 2, so it is 2 times delta of n, so the corresponding output is also going to be scaled by the same factor, so that's 2 times h of n. And when the input is delta of n minus 1, the output is h of n minus 1. Now this delta of n minus 1 is scaled by minus 3. So this delta of n minus 1 is scaled by minus 3. So the corresponding output h of n minus 1 is also going to be scaled by that same factor, minus 3. So it will be minus 3 times h of n minus 1. Now if you notice, what is this 2 and minus 3 and the 1 here? It is nothing but this x of n, right? So this is basically, we can write this as x of minus 1 into h of n plus 1 plus the 2 here is nothing but x of 0, right? So x of 0 times h of n. So it is x of 0 times h of n, and the minus 3 here, minus 3 in this equation, okay, this minus 3 is nothing but x of 1. So it is plus x of 1 times h of n minus 1. Okay, so basically we have now represented the output in terms of the impulse response when the input is shifted versions of the impulses. Okay, so this representation can now, this idea can be extended. So we have now defined our input only for the range from minus 1 to plus 1 for values of n, right? But if we had this input going further to the left and further to the right, then the corresponding output y of n will simply be terms further to the left, x of minus 2 h of n plus 2, and on the right side it will be x of 2 h of n minus 2, and so on, right? We will keep adding more terms to the left as well as more terms to the right, so that we can take it on up to infinity if we had a sequence which had an infinite length. So in general we can write it as the output y of n as we're coming from infinity, for example, and then we can have x of minus 3 into h of n plus 3 plus x of minus 2 into h of n plus 2 plus x of minus 1 into h of n plus 1, and we can add plus x of 0 times h of n plus x of 1 times h of n minus 1 plus x of minus 2 times not minus 2, that's x of 2 times h of n minus 2 plus x of 3 times h of n minus 3 plus more terms. Okay, so basically I've just extended this idea where in the previous case we took an input signal x of n having only or is defined only for the interval from -1 to 1. If we had more terms to the left and more terms to the right, then we are basically including those additional terms. So x of 0 times h of n, x of -1 times h of n plus 1, right? That's the -1 term, then the -2 term, and so on. So this is basically the response of the LTI system when the input is expressed as a linear combination of the unit impulse function, right? So in general, now we have written this as a linear combination of the impulse responses of the system, a linear combination of the shifted impulse responses, and we can write this very concisely as y of n equals summation x of k times h of n minus k for k equals minus infinity to infinity. Okay, so when k equal to -1, it will be x of -1 into h of n minus -1, which is n plus 1. So x of -1 into h of n plus 1. When k equal to 0, it is x of 0 into h of n, which is this term. When k equal to 1, it is x of 1 into h of n minus 1, which is this term. So that way we have this general expression for the output of a system in terms of the shifted impulse responses. Why? H of n is the impulse response of the system, as we have seen here. H of n is called as the impulse response of the system, and h of n minus 1, h of n plus 1, h of n minus 2, h of n plus 2, and so on, they are shifted impulse responses. So basically we are now able to represent the output of an LTI system as a linear combination of shifted impulse responses, and we are able to do so because we are able to represent our input signal x of n as a linear combination of shifted impulses. Okay, so therefore for an LTI system, let's make that statement. So what we see is that if we know the impulse response of an LTI system, we can find the response of that system to any input x of n, which is basically going to be a linear combination of shifted impulse responses. Okay, and this expression that we have for y of n here, this particular expression, let me mark it in a red box here. This is an important relationship. This is an important equation, a very, very important equation. It's called as the convolution sum of the response of a system. Okay, so we call this equation, I'm going to rewrite that equation, and so let's write that y of n is equal to summation x of k times h of n minus k for k equals minus infinity to plus infinity, and this is called as the convolution sum. This equation is called as the convolution sum, or it's also called as the superposition sum. Okay, or superposition sum. Okay, so basically this can be written in short form as this operation, or this equation can be written, this convolution operation is denoted as y of n equals the input signal x of n convolved. Okay, the convolution symbol is the star, so we write the convolution operation with the star symbol. So it's a convolution between the input x of n and the impulse response h of n of the system. So for an LTI system, the output of the system is the convolution of the input with its impulse response. So if we know the impulse response of the system, that is the output of the system when the input is a delta function, we can find the output of the signal of the system to any input signal x of n by taking the convolution of that input signal with the impulse response of the system. So that is what this equation means. So the star operator, star symbol denotes convolution operation, and this is an important operation in signals and systems as well as in signal processing. Okay, and so that's basically equal to summation x of k times h of n minus k for k equals minus infinity to infinity. So basically what we are saying here is that the output of an LTI system is the convolution between the input and the impulse response of the system. So what we see here is that the output of an LTI system to any arbitrary input x of n is nothing but the convolution of the input x of n with the impulse response of the system h of n. So that's x of n convolution with h of n, and convolution operation is defined by this summation here, which is called as the convolution sum. Okay, and so we call it as the convolution sum, also called as the superposition sum, but more often we will be referring to it as the convolution operation. Now, how to perform the convolution between two discrete sequences and also for two continuous sequences, we will do some examples on that later, and you will also come across those examples in the tutorial. But you need to understand exactly what this convolution operation is representing in terms of the relationship between the input and output of a system. So basically, we are able to represent our input signal x of n in terms of or as a linear combination of delta functions, and in which case the output of the system can also be represented in terms of the impulse responses or shifted impulse responses, right? So that is what it means, and the relationship that we get is this expression which we derived from this particular summation here, okay, which was very straightforward to arrive at. And this operation here is called as the convolution operation, which is denoted by the star operator, okay, the star symbol. And basically, if you want to find the output of an LTI system, the only thing you need to know is the impulse response of that system and what is the input of the system, right? So if you know the impulse response of a system, then you can find the response of that system to any other input signal. So if I know what is the output of my system when the input is delta of n, okay, I know it is h of n. If this is known, then we can find the output of this system to any x of n, okay? So what we see is that if h of n is known, we can find the output y of n as x of n convolved with h of n. So let me write that as well. Basically what we're saying is that if the input to this system, okay, x of n is equal to delta of n, okay, if we have, okay, I won't write it as x of n, okay, if the input to the system is an impulse, okay, is a unit impulse function delta of n, and the output is h of n, okay, so I have a system, an LTI system, and I know that when the input is delta of n, I get an output h of n. If this h of n is known, then we can find the output of that same LTI system for any other input signal. So if there is any other input signal x of n, what is the output of the system? That is what we are interested in finding. And if we know this h of n, we can find the output y of n. So the output y of n here is nothing but the let me write that clearly. So this y of n is equal to x of n which is the input x of n convolved with h of n. Okay, so if we know this h of n, which is the output of the system when the input is a delta function, then we can find the output of that same system for any other arbitrary input x of n by convolving that input x of n with the impulse response h of n. That is what it means. Okay, so how to perform this convolution operation? We'll take examples of x of n and h of n, or we can also call it as x1 of n and x2 of n, and perform this convolution operation. And we will see examples of this in the lecture. I will give very briefly, but we will do more examples in the tutorial as well. So you need to focus on these very clearly, because convolution is a very important operation, and it is used very widely in our analysis of LTI systems. So I suggest you practice in the tutorial very well regarding this convolution operation and have a clear understanding of what this means. Okay, we'll stop here for today and we will continue in the next lecture.